In section 4 of chapter 1, we're going to be going over graphing linear inequalities. But before I do that, I want to review the two basic fundamentals that those two are based off of. It's going to feel like a lot of review stuff all the way ranging back to middle school math, but it's critically important. First, I want to go over graphing inequalities. Inequalities are those little alligator symbols that you remember. Greater than or equal to, less than or equal to. I want to review this because it's going to be incredibly imperative that we understand these symbols and what they mean, so that we can then continue this from one dimensions, just having an x, to two dimensions, having an x and a y. First, I have x is greater than or equal to -2. Now, if you want, you can draw dashes and do a whole number line. I like working smarter, not harder, and just putting a single dash on my number line and saying, okay, it's at -2. If you want to, you can go right ahead and go, okay, then this is -1, this is 0, and this is 1, and this would be -3, -4, -5. If you want to do that, whatever floats your boat, but I like just having the -2. For that inequality, x is greater than or equal to -2. -2 is part of the solution. That means -2 is an answer. The graph we're about to create is supposed to be a visual illustration of all the answers. So I need a way to make sure that I recognize that -2, which is where I'm going to start, is part of the solution. The way we do that is we draw a closed dot. Now I'm about to do something that I don't recommend that you do, because the way I have this set up on my tablet is different than how you will have it set up on your tests and coursework. There are two ways that I could generate the answer from this. The first way, which I don't recommend you do, is I look for where the numbers for x is going to be bigger than -2. That's in this direction right here. Can anyone see a problem with me doing this on your paper? Yeah?
You can't see the line anymore?
I can't see the line? Yeah, why can't I see the line?
Because on your tablet it's red, but on paper it'd be gray.
Correct. You are all usually writing in either pencil or a black pen, and you're writing black on black. It's hard for me to read. I don't recommend that you draw your line on top of a pre-existing line because it gets really difficult to visualize. Here's what I generally recommend for students to do. Draw a vertical line up and then a line in the direction that you actually want to go, because then I can see what you mean, and it avoids that whole fiasco. Problem 2, same thing. I have x plus 3 less than 5. I cannot graph this until the x is isolated, so I got to subtract the 3 from both sides, leaving me with x is less than 2. Again, I'm going to work smarter, not harder. I'm not going to do the whole number line, just the 2. Because this inequality is a less than symbol, not less than or equal to, 2 is actually not considered part of the solution set. It is not an answer. If I plug 2 into for x, 2 is not less than 2. So the way we signify that is an open dot. Open dot means it does not include that number. Closed dot means it does. I'm looking for the numbers where x is smaller than 2. That's in this direction. Number 3. I got to get rid of that 1/3. The way I get rid of it, multiplying both sides by 3. That 3 and that 1/3 will eliminate, and I am left with x is less than or equal to 12. Because it's a less than or equal to sign, it includes 12, so I'm going to put a closed dot. I'm looking for numbers that are smaller than 12, which is to the left. Done. And then finally, problem number 4. I got to get the x by itself, so I'm going to add 1 to both sides to begin with. 2x is greater than 8. Then divide both sides by 2. And I get x is greater than 4. Here's the 4. It's an open dot because it's a greater than symbol. And then I'm looking for when x is greater, that'll be to the right. And now all 4 of these inequalities have been solved for in certain cases, but they've all been graphed. The next topic I want to talk about is graphing linear functions. Yes, we've done this, but now this is in slope-intercept form. So I want to do a brief little recap about this. This is y equals mx plus b format, where the last number that we're adding and subtracting, that's the y-intercept. That is where the function is going to intersect the y-axis. And then the number that we have in front of the x, we've already dealt with this before, but it is the slope. It is the rise over the run, change in y over change in x, the delta y over the delta x, the dy dx. It has a lot of different names because we use slope all the dang time, even up to and through calculus. But right now we're just dealing with linear functions. So y-intercept for this one is going to be positive 1, right here. The slope is negative 2 over 3, so it's down 2, because it's a negative 2, right 3, because it's a positive 3, down 2, right 1, 2, 3. You want to do more dots? Be my guest, but I only really need 2.
What if the slope is 0?
If the slope was 0, it would be a horizontal line, and we're actually going to go through an example like that. Number 2. My y-intercept is negative 5, so I'm going to go down 5. 1, 2, 3, 4, 5. There's my y-intercept. That's my first dot. The slope is the number in front of the x, which is 4 over 1. So from that dot, I'm going to go up 4, right 1. There's your second dot. You want to generate more, be my guest, but that's enough for me to draw a line as follows. Number 3 is the one that tends to trip up some students because they go, wait, I don't see an x. There's an x there. We just typically don't write it. You could have reimagined this problem as y equals 0x plus 7. It's the same thing. That means the slope is 0, but the y-intercept is 7. If the slope is 0, then that's the same thing as 0 over 1. So you'd go up 0 and right 1. If the slope is 0, if the function does not have an x in it, then it is a horizontal line. The purple problem is the curveball because I can't graph it right now. It's not in slope intercept form or point slope form, so I got to convert it into one of those two formats. So the first thing I'm going to do, besides rewriting it, is I am going to try and solve for y. I want to get that y by itself, so I'm going to subtract the 4 from both sides. That leaves me with 1/3 y is equal to 1/2 x minus 3. I now need to get the y by itself by getting rid of that 1/3. So I'm going to multiply the left side by 3, because they will eliminate. And I've got to multiply the entire right side by 3. Distribute the 3 to the 1/2 x and the negative 3. And you get the equation y equals 3 over 2x minus 9. And now it's in a format that we can graph nicely. The y-intercept is 9. The slope is 3 over 2. So up 1, 2, 3, right 2. Draw your line. Call it done. We are now going to be graphing linear inequalities. Notice, these are the exact same equations. The only difference between this slide and the last slide is I replaced the equal signs with inequality symbols. Yes, we have done this before in previous math classes. We are going to expand upon this topic as the chapter progresses. You will find that this is a very common theme in this class, which is the first half of the chapter is a lot of review of stuff you've done. The second half is combining them in unique ways to produce something new. So for the first one, I already went over graphing it. The y-intercept is 1. The slope is negative 2 over 3. Here's what makes it different. When graphing inequalities, if you are using a less than symbol, or if you are using a greater than symbol, the line is going to be dashed or dotted. So this is going to look like this. This is the first thing that makes inequalities, their graphs, look and behave differently than equations. There's the possibility that the line is dotted. Because just like how the open dots on inequalities represented that those were not answers, all the coordinates on that line are not answers. You could think about this as the open dot equivalent on a two-dimensional graph. All the coordinates on that line do not satisfy the original function. the original inequality. Next, we are going to shade. We're either going to shade on one side of the line or the other. There are two ways you can figure out how to do this. There's the intuitive way, which is the way that I like, and then there's the algebraic way, which you've already done before. Here's the intuitive way. When looking at the original inequality, it says that y is bigger than the line. So I asked myself, where is y going to be bigger than the line? Above it or below it? You tell me. Where is y bigger, above or below? Above. So when I shade, I'm going to shade above the line. And this is the answer. This is the answer to this problem. The other way, which is something you've done in the past, if you want to do it algebraically, is you select what's called a test point. Typically, the test point we like to pick is the origin. One caveat, the test point cannot be on the line. If it is, then your test point is going to be just superfluous. It's not going to do anything. Because my line does not go through the origin, one thing I could do is plug 0, 0 into this function. If you do that, you'll get 0 is less than negative 2 over 3 times 0 plus 1, which would turn into 0 is greater than 1. Is that true? Is 0 bigger than 1? No.
No.
Therefore, the location where we chose the test point, 0, 0, that's not going to be shaded because it produced a false statement. So this side can't be shaded. Therefore, logically, this side must be the one that's shaded. So you pick a test point. If it's true, that region is shaded. If it's false, that region's not shaded. I like the intuitive approach because you can do it in just like a couple seconds. This requires a couple steps. Number 2, I'll graph this one fairly quickly. I'm going to go down 1, 2, 3, 4, 5, which is right here. Slope is 4 over 1. And this one's going to be a solid line because the less than or equal to symbols or the greater than or equal to symbols have solid lines. You can kind of tell because they're underlined by a solid line. So this one I'm going to graph as if it was a normal linear function. And I've just got to determine which side is going to be shaded. The inequality says that y is smaller than the line. Y will be smaller below the line, so it's going to be shaded in this region because this region is below the line. There's my answer. And then problem number 3, we go up to 7, which takes us to here. Y has got to be greater than or equal to 7, meaning it's going to be shaded above because y is greatest when you're above. And then finally the purple line, y-intercept of negative 9, slope of 3 over 2. This line's going to be dotted. And because it is y is less than the line, y is less than when you are below. So it's shaded below. You can verify all those shaded regions using a test point if you so choose.